Falling into a black hole would not overwhelm you instantly. And somehow, that's the disturbing part. At first, gravity would pull harder on your feet than your head, not by a small amount. By enough to fundamentally distort the structure of your body. The difference in gravitational pull across your frame would begin stretching you. Slowly at first, then dramatically. Your spine would elongate. Your skeleton would deform. Internal structures would lose cohesion under the immense tidal stress. Eventually, you would no longer resemble a human form at all. You would become a long, continuous stream of matter stretched across thousands of kilometers while still falling inward. Astronomers actually have a name for this: spaghettification, which somehow makes the entire concept feel even stranger. But the truly bizarre thing about black holes is that this is only one possible scenario. Different black holes create completely different forms of environmental extremity. Some surround themselves with radiation intense enough to make close approach physically impossible. Some are so enormous that you could cross the point of no return without noticing anything unusual at all. Some distort time so severely that billions of years could pass in the outside universe during your descent, and some are so tiny and fast-moving that they could cross through ordinary matter almost invisibly. There is no single experience of entering a black hole. There are many, and each one becomes more unsettling than the last. The strangest part? The largest black holes may actually offer the smoothest entry conditions, at least temporarily. To understand why any of this happens, you first need to understand what a black hole really is, because the popular image of a giant cosmic vacuum cleaner is wrong in almost every important way. A black hole is not an object in the ordinary sense. It is a region of space-time. More specifically, it is a region where gravity has become so extreme that the escape velocity exceeds the speed of light. Escape velocity is simply the speed required to break free from gravity. Earth's escape velocity is about 11 kilometers per second. The sun's is roughly 620. But around a black hole, at a certain boundary, that required speed surpasses 300,000 kilometers per second, the speed of light itself. And because nothing in the universe can move faster than light, anything crossing that boundary becomes permanently trapped. That boundary is called the event horizon. It is not a physical wall. There's no visible line, no surface, no barrier you could touch. It's a mathematical threshold in space-time itself. A point where every possible future path curves inward, not because something is dragging you like a forceful hand, but because space-time beyond that boundary only permits one direction of motion, further inward. Black holes form when massive stars collapse under their own gravity. Throughout a star's life, nuclear fusion pushes outward while gravity pulls inward. Those forces remain balanced for millions or billions of years. But once the fuel is exhausted, the outward pressure disappears. Gravity takes over completely. The outer layers collapse inward at enormous speeds, triggering a supernova explosion, and if the remaining core contains enough mass, typically more than 3 suns combined, nothing can halt the compression. Matter is forced beyond the density of neutron stars toward a singularity, a region where current physics equations stop producing reliable answers. Surrounding that singularity lies the event horizon. And surrounding the event horizon in many cases is something even more hostile: the accretion disk. Most black holes are not isolated in empty space. They are surrounded by infalling gas, dust, shattered stars, and superheated plasma spiraling inward at incredible speeds. As this material compresses, friction and gravity raise temperatures into the millions of degrees. The disk radiates enormous amounts of energy, especially X-rays, often producing more luminosity than entire galaxies. The brightest quasars in the universe are powered by these feeding supermassive black holes. Approaching a stellar black hole would become physically impossible long before reaching the event horizon itself. The danger would begin with heat, then radiation. Intense streams of high-energy X-rays would penetrate matter at levels far beyond what biological systems could tolerate. Molecular structures would destabilize, cellular processes would fail, electronic systems would rapidly degrade. Long before reaching the black hole itself, the surrounding environment would already have become completely incompatible with human survival. And even with theoretical perfect shielding, the tidal forces would eventually dominate. Tidal forces are caused by differences in gravity across distance. On Earth, the moon pulls slightly harder on one side of the planet than the other, creating OC. But now consider a supermassive black hole. And here is where the physics gets genuinely counterintuitive. Supermassive black holes sit at the centers of most large galaxies. Sagittarius. A star at the center of our Milky Way has a mass of about 4 million suns. The black hole at the center of galaxy M87 is 6.5 billion solar masses. There are objects we have detected that may be tens of billions of solar masses. These giants are enormous compared to stellar black holes, but small compared to the structures around them. Here is the strange thing about these monsters. Tidal forces depend on mass and distance from the center. As mass increases, the event horizon grows proportionally. The tidal forces at the event horizon actually decrease as the black hole gets more massive. The horizon is far from the singularity, so the gravity gradient across a human body can be relatively gentle. For a sufficiently massive black hole, you could cross the event horizon without feeling anything unusual at all. No dramatic transition, no visible boundary, no alarm going off, just empty space that looks like any other empty space. You would have no way of knowing you had crossed the point of no return unless you had done the math beforehand. You would be fine for a while. The singularity of a supermassive black hole is estimated to be hours to days of falling away. You would have time to observe, to think, and to try to transmit signals back to the universe you had left. Those signals would never arrive because they would also be falling inward. You would have time to watch something extraordinary happening outside because of time dilation. Near strong gravitational fields, time runs slower relative to observers far away. This is not a metaphor, but a measured, confirmed physical effect. Near the event horizon, the effect becomes extreme. Time for you continues normally, but to distant observers, you would appear to slow redden and freeze at the horizon. From inside looking out, the universe outside would be running fast and faster than fast. Billions of years of cosmic history could unfold outside during your hours of falling and be visible to you compressed and blue-shifted. You would be watching the universe age and die while you fell through a few hours of darkness. Then tidal forces would eventually get you even in a supermassive black hole. Closer to the singularity, the gradients steepen, and the stretching would begin. By then, you would be so deep inside a region of space-time cut off from everything that the manner of your death would almost be beside the point. If stellar black holes are brutal, and supermassive black holes are vast and strange, rotating black holes are something else entirely. Most black holes spin because collapsing stars usually rotate and conserve angular momentum. These spinning black holes can rotate incredibly fast, close to their theoretical maximum. These are called Kerr black holes after Roy Kerr, who worked out their geometry in 1963. A spinning black hole does not just warp space-time, it drags it. The rotation literally pulls the fabric of space-time around like a spinning ball pulling fluid. This region just outside the event horizon is called the ergosphere. Inside the ergosphere, space-time itself moves faster than light relative to the outside universe. You cannot stand still inside the ergosphere because the dragging of space-time carries you around the rotation axis whether you want to or not. The geometry inside a Kerr black hole is structurally different from a non-rotating one. Instead of a point singularity, a spinning black hole has a ring singularity, a one-dimensional circle of infinite density. Now, let's go small. In the early universe, fractions of a second after the Big Bang, conditions were so extreme that some regions may have collapsed directly into black holes without going through the stellar process. These are called primordial black holes, and they are hypothetical but not implausible. The interesting thing about primordial black holes is that they could, in theory, be almost any mass, including very small masses, including masses so small that their event horizons would be at subatomic scales. A primordial black hole with the mass of a mountain would have an event horizon smaller than a proton. Now imagine one of these objects moving through space at high velocity. It would not interact with matter the way you would expect. It is too small for most particles to fall into it directly. It would pass through ordinary matter, through walls, through planets, through you, mostly by gravitational interaction. But as it passed through, the intense gravitational gradient at close range would disrupt matter at a fundamental level. The tidal forces across atomic distances near something that dense would be extraordinary. A primordial black hole moving through your body at speed would pass through so fast you might not register anything consciously, but the path it took through your tissue would be a line of damage, cells disrupted, molecules torn, a thin channel of destruction, a cosmic bullet you could not see, could not feel coming, and could not have dodged. They have not been confirmed to exist, but we also do not have a good way to rule them out. Some physicists think they might make up a portion of the dark matter that pervades the universe. If they do, they are drifting through space and through everything in space, including Earth, constantly and invisibly. Which is a thought you can either sit with or not. All of these deaths point at something that black holes keep forcing physicists to confront, and that physicists still do not have a satisfying answer to. What actually happens at the singularity? The honest answer is that we do not know. General relativity predicts singularities, but predicting a singularity is essentially the theory admitting it is broken. Infinite density is not a real physical description. It is a signal that the equations have hit a boundary they cannot see past. A singularity is where our best theory of large-scale physics throws up its hands. Quantum mechanics should have something to say here, but the two theories are famously incompatible. A complete theory of quantum gravity, something that would describe what happens when matter is compressed to the densest possible state, does not yet exist. Stephen Hawking's discovery that black holes slowly emit radiation through quantum effects opened a new front of the problem rather than resolving it. If black holes slowly evaporate, what happens to the information about everything they ever swallowed? The laws of physics say information cannot be destroyed, and black holes seem to destroy it. The resolution to that paradox might require rewriting our understanding of what information, space, and time fundamentally are. We built the most advanced telescopes in human history and imaged a black hole 55 million light years away. We detected gravitational waves from black holes colliding billions of years ago and billions of light years distant. We have confirmed beyond any reasonable doubt that these objects exist, and we still do not know what happens inside them. There is a boundary in the universe, the event horizon, past which no information, no signal, no light, no measurement has ever returned. Everything that crosses it is gone from our observable universe permanently. We can describe the outside. We can describe the approach. We can describe the moment of crossing for a theoretical infalling observer, but everything beyond that point is inference, mathematics, and honest uncertainty. The deadliest objects in the universe are also the most honest about the limits of human knowledge. And somewhere at the center of each one, past the event horizon, past the region of warped time and stretched light and broken physics, there is something we have no name for yet. The closest thing reality has to a doorway, and no way of knowing what's on the other side.